Hello everyone, welcome to my presentation on spatial speed accuracy trade-off in international badminton players performing the forehand smash. The conference paper for this presentation was written by myself, Idrees Afzal, Dr. Stuart McLeod-Naylor, Dr. Michael Hiley and Professor Mark King. The project's been funded by Loughborough University and the Badminton World Federation. We kindly like to thank ISBS for allowing us all to present online during this difficult time. The purpose of the study was to, number one, use Fitts' law as a model for assessing speed accuracy trade-off amongst elite international badminton players. Number two, to see if cluster analyses could be used as a robust method for comparing inter-individual performances. And finally, number three, to see how international badminton players, in terms of their speed accuracy trade-off, compared to other elite athletes from sports such as baseball, cricket, and volleyball. Over here on the left, you can see a graphic which is illustrating the early work and experimentation by Paul Fitts. You'll see that the investigators instructed the participant to rapidly aim a stylus towards a stationary target zone or area. Those two stationary target zone areas in this case being the two red rectangles on either side. You've got the letter A, which is indicating the amplitude or the distance between the two red rectangles, and you've got the letter W there, that's indicating the width or the size of each red rectangle. Commonly in this type of task, either the amplitude or the width, or a combination of both, a change from condition to condition. This is to be able to give us an idea of the movement speed accuracy trade-off used by the participant. You can see here on the right a very eloquent equation which was later devised by Paul Fitts from this experimentation. This is for a logarithmic equation for movement time, and you can see here we've got the different combinations as we've previously mentioned in terms of amplitude and width. This type of experimentation is commonly known as Fitts' law. On the left, you've got a graph with the logarithmic equation there at the bottom near the x-axis with the different combinations of amplitude and width. You can also see that here in the key above. This logarithmic equation is also referred to as the index of difficulty. And what we can see from this graph is as the index of difficulty increases, so does the movement duration in seconds. What does this tell us? Well, it tells us that there's some form of an inverse relationship between movement speed and accuracy. In terms of speed and accuracy trade-off as a human performance model, we've seen it there in terms of the handheld stylus and manual or rapid aiming tasks, but it's also been used in the sporting domain as well, in terms of projectile sports such as baseball pitching, handball throwing, soccer kicking, and Australian rules handballing. Please feel free to refer to some of these studies for further information. In terms of data collection for our project, we were very lucky to be able to collect data at the Badminton World Federation Glasgow World Championships in 2017. There we collected data on 52 international badminton players, ranked from 23 to 849 in the world. We used a Vicon 3D motion capture system to be able to collect our data. The capture frequency for this was at 400 Hz. You can see situated around the badminton court, we've got 18 infrared cameras. Those are there to be able to capture performance of the player. We've got the marker placement on the body there and also on the badminton racket that you can see. With regards to the marker placement on the body, that was for subsequent joint kinematic calculation, but actually for the purpose of this study, we just wanted to calculate shuttlecock velocity and shuttlecock landing location to be able to give us an idea of the speed and accuracy of our players. So to be able to do that, what we did was we attached 3M retroreflective tape on the racket face and on the shaft, and we also attached 3M retroreflective tape around the cork of each shuttlecock. On the right of the screen, you can see the shuttlecock launcher machine that we used at testing. This was so that we could keep the experiment as rigorous as possible. So it was a fair test, so there was no bias from somebody else was from participant to participant. So we didn't have a different type of feed for one participant and a different type of feed for another. To be able to do that, we used an international badminton player. So prior to any kind of testing taking place, we had an international badminton player select sort of an appropriate feed for a lift that would be representative for a smash. So they selected the frequency, trajectory, and power setting, and then once that was set, we used that setting for all the players. So the feed was consistent throughout. So here we've got the target for accuracy. You can see the participant aiming for the target board. You can see here we use a ratio scale with 4 concentric rings and then 1 black center circle for our scoring system. So with regards to the scoring system, any shuttlecock in terms of the smash that hit the center circle, the black center circle, was scored as 0. Anything that hit the outer rings was scored as 1, 2, 3, and 4. And then anything that hit went in the outer regions of the target board was scored as 5. And in addition, anything that hit the badminton net was also scored as 5. In terms of conditions, the first condition, the target board condition, TB, what we did was the investigator asked the participant, smash as fast as possible, but just towards the general direction of the target. For the second condition, for the center circle condition, the participant was asked by the investigator, smash as fast as possible, but this time towards the center of the target. So this, as you've hopefully noticed, is much in line with Fitz's task, where the target is often reduced in size or width to be able to give us an understanding of the speed accuracy trade-off that's been used by the participant. In terms of statistical analysis, we use a two-step cluster analysis for our investigation. You can see here the equation that we use to be able to calculate the input parameters. So we use the percentage trade-off between the two previously mentioned conditions in terms of the center circle condition and the target ball condition. The input parameters for this were shuttlecock speed and accuracy score. From the results, in terms of our findings for the exploratory cluster analysis, found that we found 3 different speed accuracy trade-off relationships being used. So you can see here the 3 different cluster groups, and on the outside of the pie chart you can also see the number of participants within each cluster. In terms of results for the shuttlecock speed accuracy trade-off, you can see here we've got the green box plot with the Fitz inverse relationship group. They generally reduce shuttlecock speed from the first condition to the second condition when the size of the target was reduced, whereas the other 2 cluster groupings, they've kept shuttlecock speed similar, or what we've seen with regards to the alternate inverse relationship group, actually they've increased shuttlecock speed. With regards to the accuracy score, speed accuracy trade-off cluster grouping results, we can see that both the Fitz inverse relationship group and the low inverse relationship group both improved in terms of their spatial accuracy generally. In terms of the alternate inverse relationship group, actually, they've either kept spatial accuracy the same from the initial target ball condition to the center circle condition, or what we've seen is actually there's been a detriment in spatial accuracy, or they've got worse from the first condition to the second. In terms of findings, findings indicate that for international badminton players, it's around 80 to 99% of maximum shuttlecock speed that seems to be the threshold for achieving the highest levels of spatial accuracy. That's much in line with some of the previous research in terms of baseball pitching and handball throwing. What's really interesting for me, I think, from this study is that actually, even within a cohort of international badminton players, we've actually found 3 different types of speed accuracy trade-off relationships being used. In terms of practical application, there's a potential here for implementing a speed and accuracy trade-off model for performance assessment in badminton, very similar to sports such as football and tennis, where they've looked at fitness testing or strength testing. Also, as we mentioned previously, coaches and players need to consider, reducing shuttlecock speed by 80 to 99% of maximum, much in line with the Fitz inverse relationship that you saw earlier in the graph. This reduction to 80 to 99% of maximum looks to be leading to a greater spatial accuracy. In terms of application for coaches, coaches should be looking to, in terms of their training design, looking to try and constrain targets by varying the width, but also the use of opposing players to be able to constrain the opposite side of the court, or some kind of a target area on the opposite side of the court for players to try and explore that speed and accuracy trade-off. In terms of future directions for us, we're now looking at the movement kinematics and movement variability of the participant in relation to their speed accuracy trade-off. That's going to be the next bit of work for us. In terms of references, please feel free to have a read and learn a few more things. And yeah, thank you so much for listening to the presentation. And if you've got any questions, I'd be more than happy to listen to them. Please get in touch. My email address is here at the bottom.